Good morning and once again welcome to my YouTube channel, Pearson and Excel International Maths by Mr. Kamoto. And today I want us to explain example 4 of pure mathematics 4 and topic number 1, and we continue to prove by contradiction. And you're supposed to prove by contradiction that there exists infinity, that there exist infinity prime numbers. That's what you're supposed to prove. When we talk about there exist or there are infinity prime numbers, we have to prove by contradiction. So we have to assumption that this is not true. And our assumption is there is a finite number of prime numbers. In other words, prime numbers reach a point and they end. That's our contradiction. Yet we're supposed to prove that the prime numbers do not end, they continue forever. What we should be able to know, as example 4 is explaining, let's just talk of list all the prime numbers that exist. Let's have the list of all prime numbers that exist. We may have prime number 1, prime number 2, prime number 3, prime number 4, all the way until prime number n. We don't know the value of n. And of course, a prime number is a number that does not have any divisor apart from 1 and itself. And this means what? If you consider a number n, which is a product of all this times p2 times p3 times p4 and all the way to pn, and then we plus 1. The reason why we have added 1 is to prove that there exist infinity prime numbers. If we have a number n that is a product of all these prime numbers, but of course plus 1, it means therefore when n is divided by any of these prime numbers, when n is divided by any of these prime numbers, we will always have a remainder 1. Let's just put it here. When n is divided by any of these prime numbers, it could be anything, p1, p2, p3, p4, all the way paka pn, you will always get a remainder of 1. Because if it's a product of this, then if it's a product of all this, then p1 is a factor, p2 is a factor, p3 is a factor, p4 is a factor, pn is a factor. But the fact that it's added, we have added 1 there, which is naturally possible, then none of this becomes a factor. We will always have a remainder 1, and therefore none of the listed prime numbers is now a factor of n, due to the fact that if you keep dividing n by any of these prime numbers, we will continue to get remainder 1, and at that point n is at that point none of these prime numbers is a factor of n. And what do you say? So n itself, so if none of these prime numbers is a factor of n, so n must either be prime, or has a prime factor which is not in the list. A prime factor which is not in the list of all prime numbers, which is very difficult. And this contradicts that if n is a prime number, and of course n is greater than the product of all the prime numbers you know. It's greater than the product of all the prime numbers you know, because the remainder is 1. Then we contradict our assumption. We contradict our assumption that there is a finite number of prime numbers. So since n is greater than the products of all prime numbers, and that n is prime number itself, then this contradicts our assumption. This contradicts our assumption, and the conclusion is there are infinite or there is there are infinite prime numbers, meaning that prime numbers do not have an end, and that is just how we are supposed to show. And it's because every scenario is naturally possible. We could have prime number 1, 2, 3, 4, and prime number n, but we could have another n which is a product of all these and plus 1, meaning that it is greater than the product of all the prime numbers listed above. And since it has no prime number, it's not divisible by this, then it happens to be a prime number. And now that it is greater than all the products, then there are infinite number of prime numbers. And that is our conclusion. Okay?